So before we get into the extension points of GraphQL, I'd like to briefly discuss what I consider the unsung hero of GraphQL. And despite the importance of this tool, it tends to get overlooked by beginners who are just starting out. I'll start first by going into exactly what problem this tool was designed for, and then go into some of the other benefits of using this in your GraphQL project. So in this example here, we are requesting a list of posts, their ID and title, and for each of those posts, we want to get the author information. You'll see over here in the result, we have 3 different posts, 2 by Andrew and 1 by Sarah. Now, the GraphQL way of resolving this query would be first to get all posts. And so the resolver for posts is likely to do a select all from our post table if we're using a SQL-based database. However, the author sub-object in this query is held in another table. And normally, if this were a REST-based request, we would probably be doing a database join using the author ID on the post table to join with the author table in order to get this information. Now that works great for REST, but sort of defeats the purpose in GraphQL because we want to be able to omit this author sub-object if we want. And if we don't need it, we don't want to make an unnecessary join to the author table. So the GraphQL approach would be to have a resolver for the posts and then a separate resolver on the author field of posts for author. And then that resolver will only execute if we actually request that field. Now this sounds great, but actually introduces a big problem that is easy to overlook. In order to run the author resolver, which is a field of posts, we first need to resolve posts in order to get that author ID. And then that author ID gets passed into the author resolver, and so we're able to get the correct author for that post. Now the problem with this is that we're actually going to have to do that first query to get posts, and then for each individual post, we'll have to do another database query to get the author information. So how this will work is first we get all posts, and then it'll run an additional 3 queries just to get the author information. And luckily, this is a one-to-one relationship, but if this were to be a one-to-many or nested further, it becomes pretty apparent that we're going to end up blowing up our database with potentially dozens of requests to resolve one specific query. This is known as the N+1 problem, because we have by default our first initial query and then an unknown amount of queries that need to take place afterwards to resolve the full query. And without a proper solution, GraphQL really doesn't scale. Thankfully, there's a way to turn this weakness into a strength, and that is by using a pattern known as the Dataloader pattern. Although it's not necessarily part of GraphQL, any language that has a GraphQL implementation also has a Dataloader implementation to be used with that GraphQL engine. Now, I'm not going to go into how to set up Dataloaders, but I am going to explain how they work. Basically, in this example, instead of executing a resolver for each individual post using an author ID from the post as an argument, what the Dataloader will do is basically collect all of these author IDs into a list. So for simplicity's sake, let's just say that Andrew's ID is 1 and Sarah's ID is 2. So that means on post, we have author ID 1, author ID 1, and author ID 2 as a field. So rather than executing resolvers, the Dataloader will collect these IDs and basically create a list of all of these author IDs for posts. In this case, it's a short list. We only have author ID 1 and author ID 2, so we only have 2 elements in that list. But if we had 100 posts here and 50 different authors, then we would have a list of 50 different author IDs. So what this Dataloader will do is first collect these author IDs, and then after the initial posts query is resolved, it'll take those author IDs and it'll do a single batch query to the database or whatever data source. It could be a REST API or a different database outside of the Post database. Regardless of where it lives, the data loader will take that list of author IDs and make a single request to get that information, and then when done correctly, map it back to the appropriate post. So instead of seeing this as an author sub-object from another table, imagine author ID 1, author ID 1, and author ID 2 as a list, and then that list, 1 and 2, makes a single database query that gets authors 1 and 2 and their information, and then it replaces that author ID 1 and author ID 2 with that information. It's a little tricky to explain, but what it essentially is doing is batching all of the authors into a single request instead of having to run for each individual post. So instead of the n+1 issue, we have a fixed 2 queries. Furthermore, the list that is provided as a data loader has to have unique keys. So that means we're not going to fetch the same author twice. So in this case, Andrew, who is the author of these 2 posts, point to the same record. And so the data loader will not request that same author twice. Instead, it'll use a unique list and then map it back. So what a data loader really is a batching mechanism that allows us to fetch a batch of objects in a single query at various depths of execution in our GraphQL query. Now, although this does solve the n+1 problem in GraphQL, thus making it a viable solution, it does come with some trade-offs. If these entities were in the same database, in a SQL-based database, for example, like Postgres, it probably would be more performant just to perform a join here. And that would reduce the 2 database queries that are needed to resolve this query into a single database query. However, there are plenty of advantages to use this rather than database joins. First off, it's not a given that these entities are stored in the same database and are even eligible for a join. This author information could come from a different database. It could come from a third-party API. It could even come from an in-memory cache. There are a variety of different sources this data could come from that would prevent us from being able to do a traditional database join. And as already mentioned before, if we're going to use database joins, it sort of defeats the purpose of using GraphQL, because if we don't need the author, then we're doing that join unnecessarily, which is going to have an added cost without the benefit. And although we could write some sort of intelligent layer to make that determination for us automatically and optimize our database query accordingly, that sort of goes against the way GraphQL was intended to be used. So although one could argue that this would not be as performant as a database join, it does have a variety of features to offset that. The best part of data loaders, however, is actually the abstraction that it provides. A data loader basically abstracts away the data fetching for a particular entity. Think of it as automating the joins in a database. It essentially enables each entity to know how to get itself as long as its primary key is provided. In fact, because the data fetching for each type of entity is abstracted away, we could even create circular queries that go to an infinite depth. An example of that would be if we wanted to get all posts for an author here. So if we did something like this, this isn't actually supported by the example schema here, but just as a demonstration. So technically with data loader, this following query would be possible, not particularly practical, but it does demonstrate how we've abstracted away using data loader the actual data fetching for these entities. Because what will happen here is we'll have our top level resolver that gets all the posts, and using the author ID of those posts, we'll get the author sub-object. And then from there, we'll get a list of all of the posts. And then using the author ID, we can get a list of posts for that author. And then again, do the same thing where for each of those posts, we get the author ID, which is circular, and then the posts for that author, and then the author for those posts. And again, not going to be the most practical or useful type of query, but it does demonstrate how we've extracted away the data fetching for each of these entities in a way that can be reused throughout the system, and that does not concern itself with the other entities in the system. It only needs the IDs that are passed in and can resolve itself from there. So this should give you a little bit of an idea of the power behind Dataloaders, how it solves the n+1 problem, which would be a deal breaker for GraphQL otherwise, and how it can be used to abstract away data fetching for a specific entity as long as primary keys are provided for that entity. And this data fetching is data source agnostic. It could be third-party APIs that support batch requests. It could be NoSQL databases, in-memory caches, or traditional SQL databases. Pretty much any data source could be used here as long as it supports batching. And in the unfortunate case that it doesn't support batching, there's also a caching mechanism that can be used. So before I end off this section on Dataloaders, I'll show you briefly the documentation for Dataloader, which really serves as a spec. This particular repo explains what a data loader is and provides a JavaScript implementation for data loader, but each individual language that supports GraphQL does have its own data loader implementation based off of this spec. If we scroll down, we can see there's some detailed documentation that you can look into. Obviously the batching function, which is really the main feature of a data loader. It also provides caching mechanisms, which would be really useful for this circular query here. Even though this isn't something that would be used in practice, it is a good demonstration of caching, because once it gets down to these levels, as long as it already has a post in memory with that specific ID, it's not going to need to request that from our data source. It'll actually pull it from cache. So this isn't a great example of how the caching would be a benefit, because this isn't a practical real-world query. But think of it as once you've fetched a resource, it is going to be cached for the remainder of that request. There are also different options for when you have one-to-one relationships and one-to-many relationships. And down here, you'll see a list of languages that do have a data loader implementation. If you want a much better and more in-depth explanation of data loaders, I highly suggest you watch this video here. Not only will Lee give a much better explanation of data loaders than me, but will actually build a data loader implementation from scratch. So you can really see how data loaders work under the hood. Very valuable video. Before we move on, I briefly wanted to show you the data loader documentation in Absinthe, which is the GraphQL engine for Elixir. You'll see here it refers to the actual specification we just looked at and explains how to set up data loaders for Absinthe. Gives a few examples, and you'll see here that the data loaders are added to the context. So that means you actually don't have to import data loaders. You pull them off of your resolution context in Absinthe, which means that they are available throughout your entire application. It can be a little tricky to get started with and take a little bit of time to get used to, but they are extremely valuable and are considered the idiomatic way in GraphQL to handle your relations.